Welcome, Hornets. In this video, we're going to be taking a look at the limit process and how we can find the integrals area or the area under a curve through this basic process. Now, I've given us some basic graph. Now, I do want to remind people that we are going to be using some basic information that you should know, and that is the limit that the summation as I approaches 1 to n for the limit, as n approaching infinity. Let's just go with the summation. This summation formula you should know as Cn. We have the summation as I goes from 1 to n of I, and this is going to be n times n plus 1 over 2. We have our summation for I equaling 1, and we have an I squared up to n. And this one is going to be n plus 1, 2n plus 1 divided by 6. And our last one that we're going to end up using at various times, I equals 1 going to n of I cubed, and this is n squared, n plus 1 squared, all over 4. Now, we'll need these as we go through this process. Just be aware of that as we go through. Now, we've talked about integrations before, and we've said to ourselves, and we said, well, we know that we are looking at intervals of rectangles. If we use the x sub I minus 1, we're going to get the inscribed rectangles, and we end up having an issue with binomials. So the binomials created inside ultimately give us trinomials. We have to then FOIL trinomials out. It makes it really ugly, and we try to avoid the x sub I minus 1. But the x sub I requires us to know how many intervals we go across. And those intervals are delta x. So no matter what you do, please remember delta x is going to always be the first thing you find. And when you get done, you get 3 over n, and it allows us to now find that x sub I, which we refer to as a c sub I. And this x sub I is 1 plus our delta x multiplied by I, which will end up being 1. Let's just identify it as a plus delta x sub I, so that we have our 1 plus 3I over n. And this is our c sub I. Now, we're going to have to put it into our definition of an integral. And according to the definition of an integral, a to b f of x dx, we are looking at the limit as n approaches infinity for our delta x times the summation as I goes from 1 to n of our f of c sub I. So we're going to make that limit as n approaches infinity for delta x times the summation, and we're going to use this bit of information to answer our questions. So here we go. The limit as n approaches infinity for 3 over n times the summation as I goes from 1 to n, and then I have my function. This function is 2 times c sub I plus 3. Now notice, I'm going to have to clean this up. So I have my limit as n approaches infinity. We're using our algebra. This is why you have to be proficient. You have to know your general skills and be kind of clean with them. 2 plus 6i over n plus 3. And you can already see that these two will add together to give you a plus 5. So we're going to separate our limit into its multiple statements using our properties, which allow us to break it up around the summation, or around the sum. So I have 6i over n. The limit is repeated. 3 over n. We put this together as the 5, I going from 1 to n. Now this 6 over n is going to come out so that we have the limit as n approaches infinity for 18 over n squared times the summation as I goes from 1 to n of I. And this is where this piece is going to now directly substitute. For this one, we have the limit as n approaches infinity for 3 over n, and this is merely our constant. So I'm going to rewrite it one more time and put it all together all at once. We're now going to do our substitution. The limit as n approaches infinity, and you'll notice that I've got 18 over n squared, and I've got two terms, n squared over 2 plus n over 2. And I'm going to want to distribute the limit to both pieces. So I'm going to have the n squared over 2 first, then I'm going to have the limit as n approaches infinity, 18 over n squared, and n over 2. This replaces with the constant, 3 over n plus or times 5n. Now we simply start applying our limits. Notice this one has them cancel, leaving us with 9, and the limit of a constant is the constant. This one, however, leaves us with the limit as n approaches infinity for 9 over n. And this one has the n's canceling, leaving me with 15. Now we can all clearly see that this has to go to 0. 9 plus 0 plus 15, leaving me with 24. The limit form will identify the area under the curve as 24. Now I would like to point out a couple of things to you. The first obvious piece is that this has to go to 0. And the only term that is going to remain is the term with n squared, the highest power, that will reduce. This is the case for all of them. In our second term here, the I squared, you'll notice that we end up with this 2n cubed over 6. We have a 4n squared. Let me try that again. That's going to give me 2 and 3. 3n squared over 6. And then we have a 1n over 6. Now the only piece that's going to end up remaining is this front piece here. All the other pieces will cancel and go to 0, just like we saw in this. And as a result, when we replace our I cubed, we're only going to want to work with I to the 4th over 4. Now, if you simplify this and you just work with it, you'll notice that I is going to have an integration of I squared over 2. So the n squared over 2 is actually acting very similar to our integration process. The I squared works with n cubed over 3, and the I cubed works with n to the 4th over 4. So please be aware of that, and we will do another problem in another video. So I will have a part 2. This is linear, finding the limit process with a linear equation. Thank you very much. Be well and be safe. and I hope all is well with you. Bye bye now.